Look up at the night sky. Every star you see is dying, slowly, over millions or billions of years. Some quickly, some patiently. Some will fade, some will explode. Stars are not eternal. They are born, they live, and they die. And in that death, which often takes longer than the age of all life on Earth, they shape everything around them. They scatter their elements into the cosmos. They light the way for new worlds to form. They become quiet companions, dim and forgotten, drifting forever through the dark. Tonight, we will follow them. We will watch the slow ending of stars like our sun, small, gentle, fading into the cool quiet of a white dwarf. We will witness the violent fury of massive stars, exploding as supernovae brighter than entire galaxies. We will visit the strange remnants they leave behind, neutron stars the size of cities with the mass of suns. We will meet the magnetars, with magnetic fields so powerful that if one came too close, it would tear apart the atoms in your body. And we will end at the singing rhythm of pulsars, dead stars that still send their messages out, billions of years after their last light was ever shown. There is no rush tonight. There is nothing to fear in this story. Just close your eyes or let them rest gently on the screen. Let your breathing slow. The cosmos is patient. It has waited 14 billion years to teach us about the deaths of its stars. It can wait for us a little longer. Welcome to Sleeping Galaxy. This is the story of when stars die. Most stars in the universe die quietly. This may surprise you. The dramatic ones, the supernovae, the black holes, the explosions that briefly outshine entire galaxies, fill our imagination of stellar death. But they are the rare exception. Most stars are small, smaller than our sun or about the same size. They are called main sequence stars. They live long, slow, peaceful lives, burning hydrogen quietly in their cores, sometimes for tens of billions of years. And when they die, they do not explode. They simply cool. They fade. They drift into a long, patient retirement. This is the story we will follow first. Imagine a star like our sun in some distant solar system. Right now, it is shining. Its surface is roughly 6,000 degrees, glowing yellow-white. In its core, every second, it converts about 600 million tons of hydrogen into helium, releasing energy that lights and warms its planets. It has been doing this for 9 billion years. It has perhaps another billion or two ahead of it, but the hydrogen will not last forever. Every star is on a schedule. The fuel in its core, no matter how vast, is finite. And as the hydrogen runs low, the star begins to change. The core, which has been releasing energy steadily, can no longer fight against the crushing weight of the star's own gravity. It begins to contract. As it contracts, it grows hotter, hot enough eventually to ignite a new kind of fusion, helium fusion, which produces carbon and oxygen. And as the core squeezes inward, the outer layers of the star do something strange. They expand. The star swells. Slowly at first, then dramatically. Over hundreds of thousands of years, it grows and grows, becoming 100, then 1,000 times its original size. It cools as it expands. Its color changes from yellow-white to deep red. It becomes one of the most strange objects in the universe, a red giant. Our Sun, in about 5 billion years, will become a red giant. Its surface will reach the orbit of Mercury, then Venus. Eventually, it may reach the orbit of Earth itself. Whether the Earth survives this expansion, whether our planet is engulfed and destroyed, or whether it drifts outward as the Sun loses mass, is still uncertain. The current best estimates suggest Mercury and Venus will be destroyed. Earth and Mars may survive, though they will be scorched, lifeless, drifting in the reddish glow of the dying star. For tens of millions of years, the star burns as a red giant, fusing helium in its core, fusing hydrogen in shells around it. Its outer layers slowly drift away into space, blown outward by gentle stellar winds. And then, eventually, the helium is exhausted too. The core, now made of carbon and oxygen, cannot fuse these elements. There is not enough heat, not enough pressure. The star is too small. So the core simply stops. The outer layers of the star, no longer supported by fusion, drift outward in beautiful expanding shells. These shells, illuminated by the hot core they once surrounded, glow in soft colors: blue, green, pink, purple, for tens of thousands of years. We call these glowing shells planetary nebulae. The name is misleading. They have nothing to do with planets. The astronomer William Herschel coined the term in 1785 because, through his telescope, the round shells looked like the disks of distant planets. The name has stayed for over 2 centuries. Some of the most famous planetary nebulae are the Helix Nebula, sometimes called the Eye of God, and the Ring Nebula in the constellation Lyra. They are some of the most beautiful objects in the universe, and yet they are something quietly tragic, the slowly expanding ghosts of dying stars. Our Sun will form a small planetary nebula, perhaps, or perhaps not. Recent simulations suggest that our Sun may be just slightly too small to ionize its expelled gases brightly enough to form a true planetary nebula. Either way, the result will be the same. As the planetary nebula drifts away, what is left at the center is the core of the star. Small, hot, dense. A white dwarf. A white dwarf is a strange and beautiful object. About the size of Earth, roughly 13,000 kilometers across, but containing the mass of a star. A teaspoon of white dwarf material would weigh about a ton on Earth's surface. Not 1,000,000 tons like a neutron star. Just a ton. Heavy but imaginable. White dwarfs are held up against gravity by something called electron degeneracy pressure, a quantum mechanical phenomenon discovered by the Indian-American physicist Subramanian Chandrasekhar. He won the Nobel Prize in 1983 for his work. He showed that there is a maximum mass that a white dwarf can have, about 1.4 times the mass of our Sun. Above this mass, known as the Chandrasekhar limit, even electron pressure cannot support the star, and something more dramatic must happen. We will return to that in the next chapter. But for now, we follow the simpler path. Our Sun and most stars will end their lives as white dwarfs. They will glow softly, white-hot, for billions of years, slowly cooling. They have no internal source of energy. They are simply releasing the heat they had at birth. Over hundreds of billions of years, far longer than the current age of the universe, they will cool. Their colors will shift slowly from white to yellow to red to a deep, dark crimson. And eventually, perhaps in trillions of years, they will fade entirely. When they fade completely, they become what astronomers call black dwarfs. A black dwarf is a star that has cooled to nearly absolute zero. It emits no visible light. It is invisible. No black dwarf has ever been observed. The universe is not yet old enough. The first white dwarfs to form, billions of years ago, when massive ancient stars died, are still cooling. They are still bright enough to detect, however dimly. The universe will need to age perhaps a quadrillion years, 1,000 trillion years, before the first black dwarf finally fades into silence. So somewhere ahead of us in deep cosmic time are the white dwarfs of today, cooling, dimming, drifting through the empty galaxies. They will outlast almost everything else. The galaxies themselves will dissolve before all the white dwarfs have cooled. The universe in the distant future will be filled with these patient, fading embers. Most of the stars you see tonight will end this way, quietly, slowly, without fire. It is, perhaps, the gentlest form of cosmic death. But not all stars die quietly. Some die in explosions so vast, so bright, that for a few weeks they outshine every other star in their galaxy combined. We call these explosions supernovae. A supernova is the most violent event in the universe, apart from the formation of a black hole or the collisions of galaxies. For a brief moment, a single dying star can release more energy than the Sun will produce in its entire 10 billion-year lifetime. There are, broadly, two kinds of supernovae. We will follow each, slowly. The first kind, Type 2 supernovae, are the deaths of massive stars. Massive stars are rare. Most stars in the universe are small red dwarfs, sun-like stars. But a small fraction, perhaps 1 in 1,000, are massive. They are stars more than 8 times the mass of our Sun. These stars live brief, brilliant lives, sometimes only a few million years, a tiny span by cosmic standards. They burn through their hydrogen quickly, then fuse helium, then carbon, then oxygen, then neon, silicon. Each new fuel burns more quickly than the last. The final stage, silicon fusion, lasts only a single day. And at the end, the core of the star is iron. Iron is the end of the road for stellar fusion. Every other element, when fused together, releases energy. Iron does not. Fusing iron absorbs energy. The moment a massive star's core becomes iron, it can no longer hold itself up. The pressure that fusion provided is gone. Gravity wins. The core collapses in less than a second. The outer layers of the star, suddenly without support, fall inward at a quarter of the speed of light. They slam into the collapsing core and rebound outward in an enormous explosion. Shock waves race through the star at thousands of kilometers per second. Temperatures reach billions of degrees. The light produced is so intense that it briefly outshines the star's entire host galaxy. This is a Type II supernova, a core collapse supernova, the death of a massive star. What is left behind depends on the mass of the original star. If the core that survives the explosion is between about 1 and 3 times the mass of the Sun, the immense pressure crushes the protons and electrons together, forming a body made entirely of neutrons. The result is a neutron star. We will visit one in the next chapter. If the core is more than about 3 times the mass of the Sun, even neutron pressure cannot hold gravity back. The collapse continues. The result is a black hole. We have already visited one of those in our previous journey. But the second kind of supernova, Type I supernovae, is different. Stranger in some ways. Type I supernovae are the deaths of white dwarfs. This may seem impossible. We just learned that white dwarfs are the quiet, fading remains of small stars. They have no fuel. They cannot explode. And yet, sometimes they do. A white dwarf in space, alone, will simply cool for trillions of years. But many white dwarfs are not alone. They orbit companion stars in binary systems. 2 stars circling each other, sometimes very closely. If the companion is still alive, a normal star or a red giant, material can flow from it onto the white dwarf. Hydrogen, helium, gathered from the companion's atmosphere. The white dwarf's mass slowly increases, and there is a limit to how much mass a white dwarf can hold. The Chandrasekhar limit, 1.4 solar masses that we mentioned earlier. If the white dwarf reaches this limit, something extraordinary happens. The increasing pressure ignites runaway carbon fusion throughout the star. In less than a second, the entire white dwarf, almost a sun's worth of carbon and oxygen, is converted into heavier elements like nickel and iron. The release of energy is so enormous that the white dwarf is completely destroyed. Nothing remains. No core, no neutron star, no black hole. Just an expanding cloud of debris, glowing brilliantly for weeks. This is a Type Ia supernova, and these explosions are remarkably consistent. Because they all happen at almost exactly the same mass, at the Chandrasekhar limit, they all produce roughly the same brightness. Astronomers can use them as cosmic distance markers. By comparing how bright a Type Ia supernova should be with how bright it appears to us, we can measure how far away it is. This is how, in 1998, astronomers discovered that the expansion of the universe is accelerating. By measuring distant Type Ia supernovae, they realized that something, what we now call dark energy, is pushing the universe apart faster and faster every billion years. The dying explosions of distant white dwarfs are how we know the fate of our entire universe. Supernovae, in their brief moments, do something else as well. In the heat and pressure of the explosion, atoms are forged together that could never form anywhere else. Gold, silver, uranium, platinum. Many of the heavier elements in the universe are made only in supernovae. Every gold ring, every silver coin, every piece of jewelry on Earth was forged inside a star that exploded billions of years before our solar system was formed. The atoms of your own body, the iron in your blood, the calcium in your bones, the oxygen in your breath, were forged in the cores of massive stars and scattered across space when those stars died. You are made of supernovae. When a massive star ends in a Type II supernova, and the surviving core is between 1 and 3 times the mass of our Sun, what is left behind is one of the strangest objects in the universe: a neutron star. To imagine a neutron star, we have to push our intuition about matter to its limit. A neutron star is the crushed remains of a star's core, packed tighter than the nucleus of an atom. It has the mass of 1 to 2 suns, but the diameter of a small city, only 20 kilometers across. 20 kilometers. About the distance you might walk in an afternoon, but the mass of an entire star. The density is staggering. A single teaspoon of neutron star material, 5 milliliters, would weigh about 10 million tons. That is roughly the weight of a small mountain, compressed into a teaspoon. Drop that teaspoon, somehow, onto the surface of the Earth, and it would fall straight through the planet, drawn by its own gravity, exiting the other side, oscillating back and forth, trapped at the center of the world. This is the density of a neutron star, so extreme that ordinary matter cannot exist there. The atoms have been crushed. The electrons have been forced into the protons, transforming them into neutrons. What remains is, essentially, one vast atomic nucleus, 20 kilometers wide. The surface of a neutron star is solid, a crust, perhaps a kilometer thick, made of iron and other heavy nuclei, packed in a regular crystalline lattice. It is incredibly strong. The crust of a neutron star is estimated to be about 10 billion times stronger than steel. Below the crust, the matter becomes stranger. Liquid neutrons. Then a soup of subatomic particles whose properties are still debated by physicists. The very center of a neutron star may contain forms of matter, quark matter perhaps, or stranger things that we cannot replicate anywhere on Earth. The gravity at the surface of a neutron star is about 200 billion times stronger than Earth's. If you could somehow stand on the surface, you would be crushed instantly into a thin layer no thicker than a sheet of paper. The light from the neutron star itself bends in unexpected ways near its surface. The intense gravity warps the path of photons. From the right angle, you could see more than half of the star's surface at once, because the light from the far side curves around toward you. These objects are not theoretical. Astronomers have observed thousands of them. They are the most numerous compact remnants in our galaxy. Estimates suggest there are about 1 billion neutron stars in the Milky Way alone. Most are silent. We cannot see them, but some are not silent. Some neutron stars are spinning rapidly, much faster than any normal star. When the core of a massive star collapses, it spins faster, like a figure skater pulling in their arms. By the time it has shrunk to the size of a city, its rotation can be extraordinary. Some neutron stars spin once per second. Some spin 100 times per second. The fastest known, a pulsar called PSRJ 1748-2446 AD, spins 716 times every second. Imagine that, a star with the mass of our sun, the size of a city, spinning 716 times per second, faster than the blades of any blender, faster than any human-made machine on Earth. When such a fast-spinning neutron star has a strong magnetic field aligned at an angle to its rotation axis, and most do, its magnetic poles sweep through space like the beam of a lighthouse. From those magnetic poles, the star emits beams of radio waves and other radiation. If those beams happen to point toward Earth, even briefly, as the star spins, we see a pulse. A pulse, then a pause. A pulse, then a pause. The star is sending us a signal, though it does not know we exist. These are pulsars. The first pulsar was discovered in 1967 by a graduate student named Jocelyn Bell Burnell, working at Cambridge University. She found a strange repeating signal, a pulse every 1.33 seconds, coming from a particular point in the sky. For a brief, magical moment, she and her colleagues wondered if they had detected an alien signal. They jokingly named the source LGM1 for Little Green Men. Then they found a second source, and a third. The sources were spread across the sky. They were not aliens. They were a new kind of star. Today, more than 3,000 pulsars are known. Some pulse so steadily that they rival the most precise atomic clocks on Earth. Astronomers are exploring the possibility of using them as cosmic navigation beacons for spacecraft far from Earth. Pulsars are the lighthouses of the cosmos. They are the dead remains of long-vanished stars still sending out their patient signals, a heartbeat that has continued, in some cases, for tens of millions of years. Among neutron stars, there is a smaller, stranger family. A subset of neutron stars whose magnetic fields are not just strong, but absolutely extreme. Magnetic fields 1,000 times stronger than ordinary pulsars, and a quadrillion times stronger than Earth's. These are the magnetars. The name comes from magnetic star. It was coined in 1992 by the astronomers Robert Duncan and Christopher Thompson when they proposed that some neutron stars must have far more powerful magnetic fields than had been suspected. Within a few years, observational evidence began to confirm their predictions. A magnetar is, in many ways, a neutron star with a temper. Where a typical pulsar might rotate many times per second, a magnetar rotates more slowly, usually once every 2 to 10 seconds. but the magnetic field around it is so intense that it actively reshapes the structure of space-time nearby. If you brought a magnetar to within 1,000 kilometers of Earth, it would erase every magnetic strip on every credit card on the planet, even from that distance. If you brought it within 1,000 miles, it would tear apart the atoms in your body. The magnetic field would be so strong that the electrons in your atoms could no longer orbit normally. Your matter would be pulled into long, thin filaments along the magnetic field lines. You would, gently, cease to exist as a coherent being. If you brought a magnetar within a few thousand kilometers of you, the magnetic field would interact with the iron in your blood. Even further away than that. Magnetars are not stable. Their immense magnetic fields slowly destabilize their crusts. The crust of a magnetar, already brittle, sometimes cracks under the strain, causing what astronomers call starquakes. These are not earthquakes. They are starquakes, sudden ruptures in the surface of a star. A starquake on a magnetar releases enormous energy. The magnetic field reorganizes itself violently. A burst of high-energy radiation is released, sometimes within fractions of a second. In December 2004, one such magnetar, known as SGR 1806-20, released a burst of gamma rays so powerful that, despite being 50,000 light-years away, it briefly affected the upper atmosphere of Earth. It compressed the magnetosphere, ionized the upper atmosphere, and even disrupted some satellites in orbit. That magnetar was on the far side of our galaxy, 50,000 light-years away, and it still left a measurable imprint on Earth's atmosphere. If a magnetar were to release such a burst from a closer distance, within a few thousand light-years, the radiation could damage planetary atmospheres, sterilize biospheres. Some scientists have wondered whether ancient mass extinctions on Earth might have been caused by distant magnetar bursts. The evidence is uncertain, but the possibility exists. There are perhaps 30 known magnetars in our galaxy. They are rare. Their active phase, when they are powerful enough to detect, lasts only about 10,000 years before their magnetic fields decay. After that, they fade into ordinary neutron stars. But there are estimated to be 30 million inactive magnetars in the Milky Way alone. The corpses of magnetars, drifting silently through space. Most of them are old, silent, dark. But some perhaps are still capable, when their crust cracks, when their magnetic field rearranges itself, of sending a final scream across the galaxy. A reminder from the dead that the universe is not always quiet. We have followed stars through their deaths. We have seen the gentle fade of small stars into white dwarfs. We have seen the explosive end of massive stars into supernovae. We have visited the strange dense remnants, neutron stars, pulsars, magnetars. And in earlier journeys, we have visited the deepest remnants, black holes. But the death of a star is not the end of its story. Every dying star, gently or violently, gives back to the cosmos. When a small star dies as a planetary nebula, its outer layers drift outward into space. Slowly, over tens of thousands of years, they spread. The gas, enriched with the carbon and oxygen the star fused in its core, mixes with the surrounding interstellar medium. It seeds the gas clouds from which future stars will form. When a massive star dies as a supernova, the giving is dramatic. The explosion scatters the star's material across light years. The gas is enriched with the heavier elements forged in the star's life and in the explosion itself. Iron, calcium, gold, uranium. The supernova ejecta becomes part of the cosmic dust. Eventually, that dust drifts, sometimes for tens of millions of years. It encounters other clouds, mixes with them. The clouds grow denser, cooler. Gravity begins to pull them together. They collapse. They warm. They begin, eventually, to ignite. A new star is born. This new star carries within it the atoms of the old one, the carbon, the oxygen, the iron, recycled, reborn, glowing in a new core. Around the new star, smaller bodies also form, planets, asteroids, comets, made from the same dust. Sometimes those planets, with the right conditions, develop oceans, atmospheres, life. Sometimes, rarely but truly, those planets develop creatures who look up at the night sky and wonder. Our solar system formed about 4.6 billion years ago from a cloud of dust and gas that had been enriched repeatedly by the deaths of older stars. Astronomers have estimated, by looking at the chemistry of our sun and our planets, that the cloud which formed us contained material from at least one nearby supernova, and probably many. The iron in your blood was forged in the heart of a massive star billions of years before the Earth was made. It was scattered into space when that star exploded. It drifted through the cold dark for a long time. It became part of the cloud that formed the sun. It became part of the Earth. It became part of you. You are made of the deaths of stars. This is not poetry. It is precise scientific fact. Almost every atom in your body, except for the hydrogen, which is older than any star, was created inside a star and then released into space when that star died. The carbon in your skin, the oxygen in your lungs, the calcium in your bones, the gold in any ring you wear, all of it was forged in stellar deaths. You are walking, right now, through your day, surrounded by, made of, the dust of vanished suns. This is the inheritance the dying stars leave us. Every supernova that ever exploded contributed, perhaps, a single atom to your body. Every white dwarf that ever cooled, every red giant that ever expanded, every neutron star that ever spun. They made the universe richer, more chemically complex, more capable of producing the things we are. We are, in a sense, the universe remembering itself. The dying stars made us. We carry them inside us every moment. We have come to the end of our journey. We have walked among dying stars. We watched a small star, like our sun, swell into a red giant, and then drift away as a planetary nebula, leaving behind a tiny white dwarf. We saw the slow cooling of those white dwarfs, over timescales longer than the age of the universe. We learned that most stars end this way, quietly, gently, without flame. Then we followed the rare massive stars. We watched their iron cores collapse. We saw their layers explode outward in supernovae brighter than entire galaxies. We learned how Type 1a supernovae are the cosmic distance markers that revealed the accelerating expansion of the universe. We visited the dense remnants, the neutron stars the size of cities with the mass of suns, the pulsars sweeping their lighthouse beams across space, the magnetars with magnetic fields so violent they can crack their own surfaces and send gamma-ray bursts halfway across the galaxy. And we ended where all stories must, with what is left behind. Every star that has ever lived is, in some way, still with us. Their atoms are in our oceans. Their iron is in our blood. Their carbon is in our skin, and our trees, and our books. Their gold is in our jewelry, mined from rocks that were themselves enriched by the deaths of more massive stars in the deep past. We are the children of dying stars. When you look up at the night sky tonight, remember this. Every star you see is slowly dying. But every star that has died before is alive in you. You are warm. You are breathing. You are made of stardust, which was once the fire of suns. The cosmos has been preparing for you for 14 billion years. And tonight, gently, it lets you rest. Sleep well. The cosmos keeps watch. Good night.